So the topic, students, which I want to discuss in today's lesson, first is the solenoid. Solenoid part we have already discussed that if you have long conductor and if you bend that long conductor in the form of a coil, many coils, that is called a solenoid. And in a solenoid, very important thing is that the length of the wire is very large as compared to the radius or diameter of a coil. What do I mean by this statement, the length? You know, there are many coils in this diagram. There are many coils. Means if you stretch this coil, and then you will find that is a very long wire, a long wire. So length is very large. Compared with what? Compared with the diameter of the coil or the radius of a coil. So basically, a solenoid means a long wire that is bent or wind in the form of a many loops whose length is comparatively large with the radius. That is solenoid. Here in the with the topic of solenoid, I want to add the topic of electromagnet. What is electromagnet, children? Electromagnet. So I want to write the heading electromagnet. Basically, electro and magnet word, if you find, with the help of the electricity, to make a magnetic materials gets magnetized. To make a magnet with the help of electricity, electromagnet. Electromagnet is a material that work as a magnet, but if the current is flowing in that electromagnet. And to make an electromagnet, we usually use a solenoid. Electromagnet is what? It is a solenoid. Solenoid is what? A long wire, many turns, many coils, very large length compared with the diameter. So this solenoid, I will consider this is an electromagnet because current is passing. Current is there. You can see in the on the screen, children. Current is passing. And doesn't matter in what direction current is passing, clockwise or not, clockwise or anti-clockwise. In what side is the north pole, in what side is the south pole. We are not worried about that because this question is not about that. We haven't to find out the direction of north and south pole. We are talking about the electromagnet actually. So electromagnet is basically a solenoid in which current is passing through, and electromagnet is used to make temporary magnet. I can write here. Electromagnet is used to make temporary, 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 what magnet? For example, children, if I take a piece of iron, I-R-O-N, atomic number 26 in periodic table, okay? If I have a piece of iron, and if I placed, means my intention is I want to make it as a magnet. It work as a magnet. It behave like a magnet. So what should I do? I will put that coil or that core, magnetic core, or that the piece of iron inside a solenoid in which current is flowing. This entire arrangement is called as an electromagnet because current is passing, and due to the current, the magnet, sorry, not the magnet, but the piece of iron, it gets magnetized. It gets magnetized. And if it gets magnetized, then that is called an electromagnet. Now, children, look again. Suppose I haven't placed a piece of iron inside the solenoid. So definitely current is there. Due to the current, the magnetic fields will be there. North and south pole will be there. Magnetic field lines will be there. Magnetic field will be there actually. But that is a weak magnetic field. And I want to increase the strength of the magnetic field. So I have different ways. Increase the number of coils, number of turns, increase the strength of the current. And third, just place a magnetic material, a piece of iron. If I place a piece of iron, then the material also gets magnetized. Now I have the two magnets. But one is the magnetic field due to the solenoid, and other the material, that the piece of iron, it's also get magnetized. So that entire arrangement is called a what? Electromagnet. So electromagnet work as a temporary magnet, means if the current is flowing, if I is flowing, I means current is flowing, not I, but the current is flowing. Okay, if the current is flowing in the circuit, then electromagnet will work. Means electromagnet will work means that if you bring some magnetic materials, that electromagnet will able to attract that material. That is the meaning. But if current is not flowing, if I is not flowing in the circuit, so immediately that the piece of iron or that arrangement won't, it gets demagnetized. And if it's get demagnetized, if current is not there, so the purpose of the electromagnet will not be there, means it cannot attract or repel the magnetic materials. Let's look some examples, children, for the electromagnet, where it is used. Here, you can find some examples here. Here, the application of electromagnet. Look at this line, children. Electromagnets are used in cranes, cranes, to sort out scrap metal pieces, door locks, motors, relays, and school belts. In all these materials that you can see on the screen, we are not going on the working how electromagnet is used to find out the sort out the scrap metals, how electromagnet is used in door locks, that you study by yourself, children. If you want to explore, you want to get more knowledge about this topic, you can study. And I want to discuss only one of the application about relay that is in our syllabus in IGCSE curriculum. Relay, children, this one. Generally, that the school bells, this might be in, if you have studied in your grade 5 and grade 6, this is a very common topic in physics in grade 5 and grade 6, grade 7 science book. School bells, electric bell. So in electric bell, that the electromagnet is used. When we press the button at outside of the door, then the bell ring. That is the working of the basis of the electromagnet, electric bell. And now, children, what is this relay? A relay. Listen carefully, 10th class students. Relay, R-A-L-A-Y. Relay is basically a switch. It is a switch. And if it is a switch, so then you know the purpose of the switch is the to on and off, to make the current flow in the circuit, or to disconnect the circuit, means switch is on or off. We have the two possibilities in a switch, either it can be on or off. There is no other third option. And so relay is used as a switch, but as relay is an application of the electromagnet. So with the help of the electromagnet, we are interested to make the circuit gets off and gets on. So that's we are going to discuss, children. Remember, children, in our house that the switch we find that are not the relay. These are the normal switch. When I press with finger with hand, so it gets on and off. But the relay is different kind of switch where we use the concept of electromagnet. Now, how does this relay work? Let's see. So again, children, before going to the working of a relay, I want to explain you the different parts which are used in a relay circuit. We have two circuits, children. The one is called the primary circuit. Primary circuit. In primary circuit, we have electromagnet. Definitely, this arrangement is an electromagnet. Electromagnet is connected with a wire, with a battery, with a switch. And here, very small current is allowed to flow. And once the current is flowed in the electromagnet, you know, again, the meaning of the electromagnet, it gets magnetized near the electromagnet. There will be strong magnetic field. Other side, we have a second circuit that is called the secondary circuit. Secondary circuit. In secondary circuit, what do we have? You can find a device that you want to operate. It may be an electric bulb, it may be an electric motor, or maybe any other higher power device that we are interested to operate. And another component you can see here, look at this part, children, this is important here. In this part, we have this kind of arrangement that the contact you can see soft iron bar is there and the spring steel is there. Now actually what happens with the help of very small current, we are interested to make that this bulb glow or lit or the motor electric motor starts working. Means with the help of a very low current or with the help of very low voltage, we are interested to operate a circuit which required very high voltage or high current or very high power devices are connected here. Now, children, let's see how does it work. Suppose the switch is closed in the primary circuit. Due to this, when the switch is closed means children remember this current is flowing in the circuit. And so around this magnet means electromagnet, somewhere north pole, or maybe let me take this is north pole, this is south pole. Randomly I have chosen here. I'm not looking for what is the direction of the current in the coil. Okay, it doesn't matter here. But the concept is that around the electromagnet, the magnetic field will be there. If magnetic field is there, children, then what happens? This soft iron bar means that is a piece of iron. It gets attracted towards the magnetic field. And if it is get attracted towards the magnetic field, then what happens as this piece of iron is connected with this point? So due to the attractive force, this switch will get in contact with the point A. If this soft iron, this bar, just consider this my right hand as a soft iron bar with the contact, which is written there. And the left hand side, that the point A, my left arm, that's the point A. Once the current is passed, so the soft iron, it's get attracted towards the electromagnet and it will make a contact with the point A like this. Once the point soft iron bar in contact with the point A, the circuit is complete. Now this is incomplete and it's a closed circuit. There is no air in the gap, no gap is there. And then in this circuit, the battery is there, the current may flow and this bulb will start working. It's not bulb, it's a bulb, it's a motor, any devices which you have connected there. So that is the purpose of a relay. Means we have used electromagnet to operate the secondary circuit. Now I want to off electric motor. I want to make the bulb get off. I want to switch off. So what I will do, switch off the electromagnet. Stop supplying the current in the electromagnet. And you know what happens in electromagnet? Electromagnet's temporary magnet. When the current is off, electromagnet, that the piece of iron that is placed inside the solenoid coil, it gets demagnetized. Once it gets demagnetized, children, then what happens? That the contact which is made at the point A, it will lose. You know, now there is no magnetic field, no magnetism left, so that the soft iron again return back because it is spring is attached there. So the spring will make that it go away from the point A. And then it means the secondary circuit will stop working as we switch off the current in the primary circuit. So that is basically a relay. Its symbol, I have to look for what is the symbol for the magnetic relay. And to draw the symbol for magnetic relay, just you need to draw a rectangular side, a rectangular block, and then you have to place a switch. But I am looking at the exact symbol for the magnetic relay. Just give me a moment. And I want to make a perfect symbol for the relay, and this is also available in your textbook and in this chapter of magnetism after topic 9.03, 9.04. Yeah, I got it. So the symbol that I want to draw here, this is a rectangular block, as I told you, and this line here, that this is for the wire, and you need to draw a switch. Okay, that's some kind of switch. So switch is here. You can draw in any way that the switch, that switch that you can make on and off. And so that basically the primary circuit, secondary circuit, the entire arrangement is for that is called the relay. Suppose if I say in exam there is a question, draw the symbol for a circuit symbol for relay. So you need to draw what? You need to draw what, children? This part. This is called a relay in a symbolical form. Like resistance, we use this. This is called the resistance. Variable resistor, ammeter, voltmeter. Similarly, that we have a symbol for the relay. This entire diagram, primary as well as secondary circuit. Now, after understanding that this relay is not such important topic, just sometime, most of the times the question asks, draw the symbol for magnetic relay, and sometimes how does it work? Just to remember it. Okay, I want to skip this question, but I want to discuss this topic now with you, children. Force on a current carrying conductor. This is the, I will say, the very first important topic, very important topic in this chapter of magnetism. Actually, each and every topic is very important, but means every time, every year, we will find some question on this topic. Force on a current carrying conductor. It's a very interesting topic, children. Force on a current carrying conductor. Look at the statement, children. Look at the heading of this topic. Force on a current carrying conductor. So this topic is giving us information that again I have a conductor, and that conductor is not, that conductor is carrying current. The conductor is not that it's not carrying current, but it's a current carrying conductor. And where it is placed? It is placed actually, that the complete heading of this topic, current carrying conductor in a magnetic field. That's right, in a magnetic field. That is the complete statement. So this current carrying conductor is placed in a magnetic field. So as per the question, they're saying, if you have a conductor carrying current, whether upward, downward, horizontal, vertical, in any direction, the conductor will experience a force. And we have to find that force, children. Now look at this question, children. Again, I hope that the heading is clear, that what we are going to find out. We have a conductor carrying current placed in a magnetic field, and we are interested to find out that a force will act on that conductor. If force will act on that conductor, it means, children, the conductor, it may move upward. If the force is acting upward, so the conductor may jump in the upward direction. If the force is acting downward, then it means that the conductor, which is placed in a magnetic field, in a uniform magnetic field, the conductor may move into the downward direction. So either upward, either downward, to the left, to the right. We are going to discuss this concept here from the topic force on a current carrying conductor. Let me show you some information about this topic. Basically, these points are almost common, children, that we have discussed in our previous lesson also. How would you increase the strength of magnetic field? Increase the current, increase the number of turns, increase the strength of magnetic field, increase the length of the wire. All these points, remember how to increase. Okay, actually here this is about the force. That if the force is acting on a current carrying conductor, we are interested to increase the strength of this magnetic force. First factor, increase the current in the circuit, increase the number of turns, or increase the number of individual wires. Increase the strength of magnetic field, because the conductor is placed where? In a magnetic field. Increase the strength of magnetic field. Increase the length of the wire. Take a longer conductor, means take a long wire placed in the magnetic field. Higher force will be there. So basically, children, there is no mathematical equation given in your textbook and in your community, but I'm interested to write down one equation that is very famous equation for grade 11, 12. And as it is not the part of the IGCSE syllabus, but still I will recommend you make a note of this equation. F equal to ILB sin theta, sin theta. It's a trigonometric function, you know, sin theta, cos theta, tan cot, but here we have sin theta. The terms are easily understandable, that F is a force. What force? Magnetic force. I is what? Current passing in the conductor. L is what? Length of the conductor. Length of the conductor. B is what, children? B is called the magnetic field. It is magnetic field. What is this theta, children? Theta is very important here. This theta is going to be very, very important in this topic. Theta is called an angle. Theta is always an angle. But this angle between what? This is the angle between current I and magnetic field. Please remember, and magnetic field B. I and B. Theta is an angle between current, direction of current, and the magnetic field. And one thing, children, I'm telling you, please remember, to experience or to observe the force on a current carrying conductor, so conductor should be placed, please listen carefully, children. Conductor should be placed perpendicular to the magnetic field. Why I'm telling you this? Conductor should be placed perpendicular to the magnetic field. If you place conductor perpendicular to the magnetic field, so it means the angle between current and the magnetic field is 90 degrees. And if angle theta is 90 degrees, then what is sine 90? It's a mathematical, children. I hope you are aware about the trigonometry. If you don't know, calculate in calculator. Sine 90 degrees is 1. So the force will be maximum. If you keep the conductor perpendicular to the magnetic field, the maximum force will act on that conductor. And if you place the conductor parallel, suppose this is a, let me erase this point here, and let me make, this is the magnetic field lines. I have also told you that you can draw the magnetic field lines with the cross and the dots. So this is the uniform magnetic field, and I have placed the conductor. Suppose this is my conductor. Length of the conductor is AC, that is equal to L, and the current is going towards the magnetic field, or maybe anti-clockwise the magnetic field in any way. If I place the conductor parallel to the magnetic field, so in this case, what is the angle between current and magnetic field, children? Anyone from 10th class? May I know the angle between current and magnetic field? Both are parallel, both are in the same direction. So what will be theta? 10th class students. Tenth class students, may I know the what is the angle between I and magnetic field? Both are parallel.
Wait, sir, what's the question? What's theta?
I'm looking for that if conductor is placed parallel to the magnetic field, so what is the angle between current and magnetic field? Theta is how much? Ananya said it's a 180 degree. I'm saying that the current and the magnetic field, they are in the same direction. So they are parallel. So theta is equal to 0 degree. Children, you are not replying. It means you are very, very weak in mathematics. You don't know mathematics. It means you don't know trigonometry. If you are weak in mathematics, so you will be weak in physics also. You can't do these questions. Sorry to say this, but you're not replying here. Both the vectors, parallel vectors, vector concept, you already studied the grade 9 also. Vectors are parallel. If vectors are parallel, theta is what? Parallel and angle is 0. Theta is 0 degree here. And even if I place the this conductor anti-parallel to the magnetic field, theta is 180 degree. So if theta is 0 degree or 180 degree, again by the equation F is equal to ILB sine theta, and theta is 0, sine 0 0. I don't know how many students know that the sine 0 is 0, but sine 0 is 0. So sine 0 is 0, then the force is 0. It means the conductor, once it placed parallel to the magnetic field or anti-parallel to the magnetic field, it won't experience any force. The conductor will remain as it is. Neither it will move upward, downward, left or right. It will remain here. But actually, children, our topic, we are interested to find out the force. Okay, it's okay. With 180 degree also, this angle, still the force is 0. Good. I appreciate that you have replied. Now, children, now the question is, we are interested to find out the force. And to find out the force, you have to use a rule that is called the Fleming left hand rule. And let me explain the Fleming left-hand rule, children. To find out the direction of force on a conductor placed in a magnetic field, there is a law, there is a rule that is called, children, Fleming left-hand rule. And left hand means left hand. This is my left hand, and you have to arrange your left hand in this way, that the thumb, first finger, and second finger, all other fingers should be according to this diagram. So thumb, you need to stretch thumb, first finger, and second finger. First finger, index finger. Second finger, middle finger. So please remember these names. Now, children, I will encourage you that on thumb, if you can write F on the screen also you can see, but try to write down so that you can remember for this day. F, I have written F here. On the first finger, that is called the index finger, I will request you to write down M, letter M. I will explain what is this F, what is this M. And on the middle finger, children, the taller finger, and on it please write down C. So these three letters F, M, and C are for father, mother, and child. This is a rule, a shortcut method, a trick to remember. F father, M mother, C child. So what is this F here? What is the father actually? F. This F is for the magnetic force that we are looking for it. Magnetic force. I have written M. M for the magnetic field. M, magnetic field, children, which is represented by letter B. Okay, so the first finger for the magnetic field, third finger, not the third finger, the second finger, that is the middle finger. Okay, for C, or current, direction of current, children, current, or even that according to this book on the cognitive, father, B, magnetic field, or I. Better to write, remember in the terms of father, mother, child. So let me give you a problem, and then we have to work on it, that how would I find the direction of force on a conductor placed in a magnetic field. Now children, this is a situation. And in this situation, a conductor, you can see children, current carrying conductor. It's a current carrying conductor. There is no sense of force, no force. If the current is not there, no force. Force will not be there. Conductor should carry a current. Okay. So this is a current passing in the conductor in this direction. Where is the magnetic field? Magnetic field is produced with the help of the bar magnet. North and south pole is there. And the magnetic field lines move from the north to south. These are the direction of the magnetic field lines. And now children, we have to find the force. Even that the answer, they have solved this question, the problem has been solved. Direction of force is acting downward, but we will try to find out how this sign of red line is acting downward. Okay, now children, let me explain first. Fleming left-hand rule. So according to the Fleming left-hand rule, the first finger, which I have written M, magnetic field, it is pointing as per the screen from left to the right side. Children, left to the right. Left side to the right side. So I will arrange, or I will align my first finger in the direction of magnetic field. So this is my finger that is representing the magnetic field. So it is pointing from left side to the right side as per the diagram on the screen. Then look for the current. In what direction the current is going, children? This current actually, this is a two-dimensional picture, and the current is actually entering into my laptop screen. So the second finger, that is called the middle finger, this one, children. This middle finger, you have to arrange this middle finger in the direction of current. So to align this finger, the middle finger in the direction of current, I have to rotate my hand, and still the magnetic field is to the right side. And I am make my hand, and this finger, the middle finger, is now moving away from me, means entering into the laptop screen. I have arranged this because as per the diagram given on the screen, children. And look at the thumb. Thumb is for F is written. F is written, direction of force. So on this conductor, basically a force will act in the downward direction. Due to that force, this conductor, it may jump, or it will try to move or try to accelerate in the downward direction. That's a miracle. It's a magic. You can show this activity to your parents, to your friends. You need a magnet, you need a wire, a copper wire, a thin copper wire you can use. Place that conductor. Yeah, definitely current should pass through. So you need an external circuit that the battery is required to make the current pass through the conductor. And then you will experience conductor will either jump downward or upward. If you reverse the direction of current, suppose instead of current going inward, let me take that the current is now moving outward towards me, children. Okay, we have 1.5 minutes for this meeting, children, so let me complete this. So I have changed the direction of current, children. Still magnetic field is same to the right side, but now the current is coming, sorry, magnetic field should be to the right side, and the current is coming to me. This finger, that children, this is pointing towards me. The middle finger is pointing, and look at the direction of thumb. Magnetic force is acting upward. So in that situation, the sign of arrow that the magnetic force will be in the upward direction. Even there is one more possibility, children. Still the current is suppose entering into the screen, but you have changed the magnetic field direction. So suppose south pole is there, this is south, and this is north pole, that these lines will change. So again, that the direction of magnetic force will also get changed. Please remember, you can also do it. So we will continue with this topic, children. Let me end this meeting first here.